Hello everyone, I am Dr. Sirajul Akfazi. I welcome you in my YouTube channel. Today in this video, I am going to talk about heterocyclic compound. So look at the molecules which is an examples of heterocyclic compound. Azepine, indole, acridine, quinoline, isoquinoline, 5-member ring, pyrrole, pyrazoles, imidazole, furan, oxazoles, thiophene, thiazoles, pyridine, pyrimidine, and purine. Now, look at here pyrrole. The aromaticity, you can see the orbital picture and unhybridized p orbital. You know pyrrole have 4 carbon, 1 nitrogen, all are sp2 hybridized. sp2 hybridized is planar, it make a planar pyrrole structure. Each ring atom also contains unhybridized p orbital that is perpendicular to the plane of sigma bond. P orbitals are parallel to each other, so overlapping between p orbital is possible. The total number of non-bonding electrons are 6, 4 of 4 carbon and 2 from 1 nitrogen. The resonance of 6 electrons follow the Haeckel's rule, so pyrrole is aromatic. Look at here, tautomerism, 1H pyrrole, 3H pyrrole and 2H pyrrole. Hydrogen bonding, intermolecular and intramolecular. Look at the synthesis, pyrrole synthesized from furan, and if you change the reaction condition like primary amine and aluminum oxide, you will get the substituted pyrrole. Pal-Nord synthesis, you can see how 1,4-dicarbonyl compound converted into substituted pyrrole. So mechanisms, you can see Pal-Nord synthesis. So look at here the step by mechanisms. Breaking of double bond and attacking on nucleophile. Then you can see the positive charge on nitrogens, and after many steps you will get the pyrrole. Hunch pyrrole synthesis, you can see alpha ketone and activated ketones, it will give the pyrrole ring. This is the steps of mechanism. Nord synthesis, you can see alpha amino carbonyl compound, activated ketone, it gives the pyrrole ring. This is the mechanism. Electrophilic substitutions, you can see C2 position is important in comparison to C3. C2 attacks give more resonance contributing structure than C3. Extra stable contribution structure generate upon C2 attack. You can see the energy diagram shows C2 attack forms more stable intermediate than C3 in C2 preferred over C3. Now electrophilic substitution, you can see 3H pyrrolium ion formation, 2H pyrrolium ion, and formation of 2 nitro, 1H pyrrole, 2 pyrrole sulfonic acid, 2 chlorosubstituted pyrrole, and 2 substituted acetyl. Reductions, you will get the 2 product in different condition, 2,5-dihydropyrrole and pyrrolidine. Remertimen reactions, you can see the reaction with the chloroform and QH, you will get the aldehyde and 1H pyrrole 2 carbaldehyde. Further, if you have this type of, then ring expression occurs and 3-chloropyridine will form. Now reactions of pyrrole, you can see the Grignard reactions, and after Grignard reaction you get 2-ethyl 1H pyrrole and 1H pyrrole 2 carboxylic acid. So medicinal uses, glycopyrrole, anticholinergic drugs used in peptic ulcer, atorvastatin used in the management of high cholesterol and high blood pressure. Now furan, aromaticity, you can see sp2 hybridized orbital and unhybridized p orbital. So furan have 4 carbon and 1 oxygen, all are sp2 hybridized. sp2 hybridized is planar, it makes a planar furan ring structure. Each ring atom also contains unhybridized p orbital that is perpendicular to the plane of sigma bond. Here p orbital are parallel to each other, so overlapping between p orbital is possible. The total number of non-bonding electrons 6, 4 from 4 carbon and 2 from 1 oxygen. The resonance of 6 electron follow the Haeckel's rule, so furan is aromatic. So Paul-Nord synthesis of furan 1,4-dicarbonyl compound. You can see the cyclization occurs. This is the steps of mechanism. First, binary synthesis, reactions of alpha haloketones with beta ketoester in the presence of a base, not ammonia, to give furan. Alpha haloketones, activated ketone, you will get the furan. This is the mechanisms. Now, from carbohydrate, distillation of CH with the sulfuric acid, and then catalytic decomposition of furfural in steam, pentose, furfural, steam, calcium oxide, will get the furan. Electrophilic substitution, furan undergo electrophilic substitution reaction at second position. So C2 attack give more resonance contributing structure than C3, extra stable contribution structure generate C2 attack. So C2 is very important. Electrophilic substitution, you can see it react with the protons, and after ring opening it gives succinaldehyde. Now electrophilic substitution at 2 position, 2-nitrofuran and 2,5-dinitrofuran, same as sulfonic acid, chlorination at 2 positions with acetic anhydride acetyl group at second position. Reductions, tetrahydrofuran. Now Diels-Alder reactions, O atom is highly electronegative, so the delocalization of lone pair of electron in aromatic system of furan is not overly effective. Thus furan can behave as a dienophile and gives 4+2 cycloaddition. Look at here, dimethyl malate. It react with the furan, it gives adduct. Now Diels-Alder reaction, malic anhydride react with the furan forming adduct and 2 product XO into. Now you can see the pyrrole synthesis. Pyrrole you will get from furan. Now medicinal uses, nitrofurans, nitrofurazones, furazolidine and nitrofuradoin, anti-ineffective agents used as an antiprodual agent to treat tryptosomaniasis and leishmaniasis. You can see this compound contains nitro groups, imine and furan. Ranitidine, antihistaminic agents used in peptic ulcer. You can see it contains furan rings. Now thiophene, aromaticity. You can see sp2 have dies orbital like furan and pyrrole and have dies p orbital. So aromaticity, thiophene have 4 carbon, 1 sulfur, all are sp2 hybridized. sp2 hybridization is planar, it makes a planar thiophene ring structure. Each ring, atoms also contains unhybridized p orbital, and that is perpendicular to the plane of sigma bond. And same as total number of non-bonding electrons are 6, 4 from 4 carbon and 2 from 1 oxygen. The resonance of 6 electron follows the Haeckel's rule, so thiophene is aromatic. Now you can see the furan is less aromatic, thiophene is more aromatic, and this is the order of aromaticity. Benzene greater, then thiophene, then pyrrole, and then furan. So resonance energy, you can see only 16 in case of furan, and in case of this pyrrole 22 and 29, in case of benzene 39. So this order depends on the order of electronegativity of heteroatoms. The more electronegative is the atom, the more tightly hold the lone pair of electron, more reduce the easy of delocalization, aromaticity. So most electronegative oxygen in furan most decreases aromaticity, and least electronegative sulfur in thiophene least decreases in aromaticity. Now Paul-Nord synthesis of thiophene, as usual, you can see this is the mechanism. From sodium succinate, you will get the ring. Hinsberg synthesis, you can see the starting compound, 1,2-dicarbonyl compound. Thiodiacetate, you will get the thiophene diketone. Now reactions, electrophilic substitution also occurs here. Carbon 2 position. C2 attack gives more resonance contribution structure than C3. Extra stable contribute structure generate upon C2 attack. So reaction, electrophilic substitution, very strongly acidic condition lead to acid catalyzed polymerization. You can see in case of sulfuric acid, it gives the polymerized structure, phosphoric acid. The action of hot phosphoric acid on thiophene lead to a trimer. Now the reactions, electrophilic substitution, you can see 2-nitrophene major product, sulfonations at 2 position, chlorination at 2 and 5 position, acylation on 2 position. Now reductions, it will open the ring and form butane, and it will reduce all bond forming tetrahydrothiophene. Now you can see the reactions. You have the thiophene to thiophenylithium, and after reaction with the carbon dioxide, thiophene to carboxylic acid. Now medicinal uses, sitacentoin and cardiovascular agent used in the pulmonary artery hypertension. Tiagabeans, anticonvulsant agent used in the treatment of epilepsy. You can see the thiophene group is there, and in centofen, you have the thiophene and other ring is also present. Now, articaine anesthetic agents, you can see the thiophene is present. Now, pyrazoles, look ahead here, pyridine-like nitrogen and pyrrole-like nitrogen, both types of nitrogen. Pyridine and pyrrole. Here sp2 hybridized orbital and unhybridized p orbital. Pyrazole have 3 carbon, 2 nitrogen, all are sp2 hybridized. sp2 hybridization is planar, it makes planar pyrazole ring structure. Each ring atom has also contains unhybridized p orbital, and that is perpendicular to the plane of sigma bond. Here p orbital are parallel to each other, so overlapping between p orbital is possible. The total number of non-bonding electrons are 6, 3 of 3 carbon, 1 from 1 nitrogen and 2 of the other nitrogen. The resonance of 6 electrons follow the Haeckel source, so pyrazole is aromatic. Here you can see the tautomerism of pyrazoles, hydrogen bonding, intermolecular, intramolecular. You can see the synthesis, pyrimidine give the pyrazole after ring contraction. Look at these mechanisms, how ring contractions, oxazoles is forming, and binucleophilic additions, ring opening, and then ring closure. Non-pyrazole synthesis, you can see reaction with hydrazine, 1,3-dicarbonyl compound, it gave the pyrazole. You can see the steps of pyrazole synthesis. You can also see non-pyrazole synthesis, unsaturated dicarbonyl compound will give the 2 isomeric structure. Now, pyrazoles are produced by the dipolar cycloaddition between alkyne with nitrilamine. This is the nitrilamine like alkyne. So, from diazo compound, you will get the pyrazoles. Now, reaction, electrophilic addition to nitrogen and protonation basic properties, you can see pyrazolium cation. Now, electrophilic substitution nitrogen and alkylations, you can see N-methyl, dimethyl pyrazonium salt. Pyrrole as a base remove protons, and then you will get the salt. Now, electrophilic substitution to nitrogen in alkylation. You know pyrazole react with alkyl halide and first give N-alkyl pyrazolium salt, and this salt can lose an N proton in an equilibrium with unreacted pyrazole generate N-alkyl pyrazoles. Now, N-alkyl pyrazole react with alkyl halide and gives N1 into dialkyl pyrazolium salt. Now, electrophilic substitution to carbon. You can see the pyrazole undergo electrophilic substitution reaction at 4th position. So electrophilic substitution at possible position with intermediate, you can see carbon 3, you can see carbon 5, you can see carbon 4. So intermediate with positive azomethane nitrogen, highly unfavorable. So fourth positions is important in case of pyrazoles, and that is NH will get the 1 position into second, 3 positions, and 4th position and 5th position. Now you can see the electrophile attack at carbon 3 and carbon 5 generate highly unstable positively charged azomethane intermediate. Electrophilic attack at carbon 4 complete without any such highly unstable intermediate. Thus, transition is much higher for the carbon 3 and carbon 5 attack than C4. So, electrophilic attack takes place readily at the neutral or alkaline media as pyrazole protonated. Pyrazole is more resistant to the electrophilic attack than pyrazole. So, look at here the nitro substitution, iodination, and bromination. Oxidations, you can see ring, nothing happen on ring, reductions, and removal of double bond. So formation of phenyl pyrazolidine and 1-phenyl 4,5 dihydropyrazoles. Ring opening, N-substituted pyrazole reacted with a strong base sodamide cause ring opening. You can see N-substituted pyrazoles ring opening, you will get this acrylonitrile derivative. Now, medicinal uses, many synthetic pyrazole compounds are of importance as dyes in medicine. Antipyrine used as an antipyretic, analgesic, tetrazine as a yellow dye for food, phenylbutazone an anti-inflammatory drug. You can see the structure of antipyrine. Antipyrine contains pyrazole and phenylbutazones, it contains pyrazole. Now imidazole, pyridine-like nitrogen and pyrrole-like nitrogen. This is the orbital diagram, unhybridized p orbital and sp2 hybridized orbital. Now aromaticity, you can see imidazole have 3 carbon, 2 nitrogen, all are sp2 hybridized. sp2 hybridized is planar, it makes planar imidazole ring structure. Each ring atom also contains unhybridized p orbital and that is perpendicular to the plane of sigma bond. Here p orbitals are parallel to each other, so overlapping between p orbital is possible. The total number of non-bonding electrons are 6, 3 of 3 carbon and 1 from 1 nitrogen and 2 of other nitrogen. The resonance of 6 electrons follow the Haeckel's rule. So tautomerism, you can see the imidazole with a ring nitrogen, hydrogen are subjected to tautomerize and hydrogen bonding. Now synthesis. Radzyszkowski imidazole synthesis. You know synthesis of imidazole from dicarbonyl and aldehyde and ammonia. The reaction complete in 2 steps and this is the dicarbonyl compound amine and diamine will form and with the reaction with aldehyde it gives the imidazole. So from alpha halocarbonyl compounds you will get the substituted imidazole. From amidine, you will get the substituted imidazoles. Now, from dehydrogenation of imidazoline, condensation of 1,2-diamine with nitrile give imidazoline. You know the imidazoline reaction with barium magnet yield 2 substituted imidazole. You can see here imidazoline here. Now, electrophilic addition to nitrogen, protonation, basic property. Imidazole except proton act as a base. So this you can see in imidazolium cation. Now in alkylations, you can see N-methyl imidazolium salt and imidazole as base remove protons and it takes methyl iodide, it gives N1, N3 dimethyl imidazolium salt. Now in alkylations, imidazole react with alkyl halide and first give an alkyl imidazolium salt and this salt can lose N proton in equilibrium with unreacted imidazole, generating N-alkyl imidazole. N-alkyl imidazole react with alkyl halide and give N1, N3 dialkyl imidazolium salt. Now you can see electrophilic substitution to the carbon, which is a favorable 4 and 5 position. Carbon 2 substitutions not favorable as it forms highly unstable N positive. So nitrations occurs, you can see, at the fourth positions, 4 or 5 dinitroimidazoles, and sulfonation occurs imidazole sulfonic acid. Halogenation, you can see Br2 in acetic acid, it gives the 4 bromo 1H imidazole. Bromination gives 2, 4, 5 tribromoimidazole. 4 or 5 bromoimidazole can be obtained by reductions of tribromoimidazole with sodium sulfide. Now you know imidazole catalyze ester HL. You know imidazole group of histidine residue present in hydrolytic enzyme function as ester HL. So imidazole as base catalyze activate water for attack at carbonyl carbon. You can see here the formation of imidazolium. You know imidazole as nucleophile catalyst. Imidazole directly attack at carbonyl carbon. You can see here and forming this type of chemistry. Now medicinal uses of imidazole: azole, antifungal agent, ketoconazoles, mycoconazoles, and clotrimazoles. Mycoconazoles, you can see the structure which contains imidazole. Antihistaminic drugs, cimetidine, used to treat the prevent peptic ulcer, gastroesophageal reflux disease, and heartburn. Antiprotozoal agent, metronidazoles, used in the hematic dysentery. You can see it contains the imidazole. Now, you can see the pyridine here, pyridine. So, azathioprines, an immunosuppressive or anti-metabolic prodrugs, anti-cancer agent, and immunosuppressive agents. This contains imidazole ring. Now, oxazoles, you can see the aromaticity, pyridine like nitrogen and furan like oxygen. So, sp2 dihybrid orbitals, sp2 hybridized orbital, and unhybridized p orbital. You know oxazole have 3 carbon, 1 nitrogen, 1 oxygen, all are sp2 hybridized. sp2 hybridization is planar. It makes a planar oxazole ring structure. Each ring, you know, atoms also contains unhybridized p orbital, and that is perpendicular to the plane of sigma bond, plane of ring. Here p orbital are parallel to each other, so overlapping between p orbital is possible. The total number of non-bonding electrons are 6, 3 of 3 carbon, 1 from nitrogen, and 2 of oxygen. So, however, an oxygen atom is highly electronegative, so delocalization is not overly effective. Now, Robinson-Gabriel synthesis, cyclizing dehydration, acid catalyzed closure of an alpha acyloamino carbonyl compound. Look at here, alpha acylamino carbonyl compound, it gives oxazole. This is the mechanisms. Now, another method from an alkyl hydroxycarbonyl components, you can see the substituted oxazole. This is alpha hydroxy and formamide. It gives diethyl oxazole 4,5-dicarboxylate, and then after decarboxylation, in presence of quinoline and copper, you will get the oxazole. From isocyanate, you can see acetyl chloride. In presence of butyl lithium, it will give the substituted by the oxazole. Now, protonation, basic properties, and electrophilic addition to nitrogen. So, oxazolium cation. Electrophilic substitution to carbon, less reactive due to oxygen present in heteroskeletal. Reaction is possible at fifth position of ring is activated by electron donating groups, and nitrations and sulfonation are more difficult. Look at here 2-phenyl oxazoles, NBS in bromosuccinamide, it gave 4-bromo 2-phenyl oxazole. So, Diels-Selder reaction act as diene oxazoles 4 pi component. Oxygen atom is highly electronegative, so conjugated double bonds are readily available as a diene in Diels radiation. Oxazole readily undergo Diels-Helder type cycloaddition across the 2,5 position. This is the example of synthesis of furan from oxazole. This is the mechanisms. Now, Kondrativa pyridine synthesis. Synthesizing pyridine derivative by Diels-Helder cycloaddition between an azadiene and dienophil, followed by an exclusion of the resulting breach of the bicyclic intermediate, the formations of pyridine from oxazoles. Now you can see the mechanisms and ring expansion. So medicinal uses antifungal agent bengazoles are natural product with two oxazole groups. You can see the two oxazole ring present in bengazoles. Oxaprozine is an steroidal anti-inflammatory agent used in systematically treat inflammations, pains, and rheumatoid disease. You can see the ring oxazole present in oxyparazine. Now, thiazoles, you can see the ring pyridine like nitrogen and thiophene like sulfur and orbital diagram. So, thiazole have 3 carbon, 1 nitrogen, 1 sulfur, all are sp2 hybridized. sp2 hybridization is planar. It makes a planar thiazole ring structure. Each ring atom also contains unhybridized p orbital that is perpendicular to the plane of sigma bond. Here p orbital are parallel to each other, so overlapping between p orbital is possible. The total number of non-bonding electrons are 6, 3 of 3 carbon, 1 from nitrogen and 2 of sulfur. The resonance of 6 electron follow Hawkins rule. Now, Gabriel synthesis from alpha acyl carbonyl compound. This is the mechanism. Now, from an alpha hydroxy carbonyl compound, hence triazole synthesis. Now, from an alpha hydroxy carbonyl compound, hence thiazole synthesis. Now, from thiocyanate salt, chloroacetones, thiocyanate salt, it gives 2-hydroxy 4-methyl thiazoles. So, electrophilic addition to nitrogen, protonation, basic properties. You can see formation of thiazonium salt and formation of N-methyl thiazonium salt. Electrophilic substitution to carbon favored 4 and 5th position. You can see the formation of 2 bromo 5 bromothiazoles, 2 amino 5 bromo thiazoles, and another 2 substituted product. Sulfonation, thiazole 5 sulfonic acid and 2 amino 5 bromothiazole. Now reactions, you can see 2 amino thiazole, it gives thiazole 2 diazonium, and after reaction it gives 2 chlorothiazole. So medicinal uses of thiazole, famotidine and nizatidine used in peptic ulcer. You can see nizatidine and famotidine. Chloramithazoles used in sedative hypnotics, and vitamin B1 thiamine used in thiamine deficiency. You can see that vitamin B1 also contains thiazole ring, and thiazole ring also present in chloromethathiazoles. You can see the sulfathiazoles antibiotic, phenytolenol anti-inflammatory, and combidazoles fungicidal that contains also thiazoles, aniridazoles chinozoomycidal drugs, it is also contains thiazole. Now pyridine, you can see the pyridine structure. You know pyridine have 5 carbon, 1 nitrogen, all are sp2 hybridized. sp2 hybridized is planar, it makes a planar pyridine ring structure, and each ring atom also contains unhybridized p orbital that is perpendicular to the plane of sigma bond, where p orbital are parallel to each other, so overlapping between p orbital is possible. The total number of non-bonding electrons are 6, 5 of 5 carbon and 1 from nitrogen. So you can see the basicity of nitrogen, pyridine and pyrrole. You can see the pyridine, benzene and pyrrole. So pyridine is more basic than pyrrole. Why? Pyridine nitrogen have lone pair of electrons, some same plane of the pyridine hybridized orbital plane. So it is not participating to the resonance phenomenon. Lone pair is readily available for acid-base reaction. Pyrrole nitrogen have lone pair of electron perpendicular to the plane of pyridine hybridized orbital plane. It participated in the delocalization of lone pair, not readily available for acid-base reaction. As lone pair of electron of pyridine are readily available than pyrrole, pyridine is more basic than pyrrole. Look at here, pyridine is less basic than aliphatic amines. You can see the pyridine and aliphatic amine. sp2 hybridized nitrogen is more electronegative, more S character than sp3. So lone pair of electron more closely held towards more electronegative nitrogen and less available for acid-base reaction. So as lone pair of electron is not readily available in pyridine, it is less basic than aliphatic amine. Now, tautomerism. Tautomerism structure is involved when pyridine substituted at second and fourth position with groups such as XH. You can see the hydrogen bond donor, hydrogen bond acceptor, and hydrogen bonding. Hence, pyridine synthesis, you can see the steps. This is the mechanism. Hence, pyridine mechanism. And Gaudeshi synthesis, modification of Hence synthesis, use of cyanoacetamide as the nitrogen containing compound. From 1,4,5 dicarbonyl compound, you can see the formation of substituted pyridine. From oxazole Kondratyeva pyridine synthesis, you can see the oxazole react with the alkene, it form the pyridine. Now reactions, electrophilic addition to nitrogen, protonation occurs at nitrogen, and alkylation occurs at nitrogen. So imidazole is approximately 100 times more basic than pyridine. You can see the formation of pyridinium chloride and formation of imidazolium cation is resonance stabilized. Now electrophilic substitution to carbon. Pyridine gives electrophilic substitution at third position. N is electronegative, so positive charge on nitrogen destabilizes the structure. Here attack at carbon 2, carbon 4 generate N positive intermediate, less favorable. So third position is important. You can see the formation of 3-nitropyridine. This is in third position. Sulfonic acid, third position. Bromination occurs, third position. Chlorination on third position. So 3-bromopyridine is produced in good yield by the action of bromine in oleum, and chloropyridine can also produce by chlorination in the presence of aluminum chloride. Now you can see nucleophilic substitutions at 3 position and 2 position. So especially stable and 2 position. So attack on carbon 2 position give more stable intermediate. A reaction with pyridine with sodamide at high temperature. This reaction is Chichi-Bevin reaction. You can see the mechanism. Pyridine as nucleophilic catalyze, you can see the formation of ester and then formation of piperidine after reductions of double bond. Now use of pyridine in medicinal uses, anti-tubercular agent, isoniazide, you can see the structure, antibacterial agent, sulfapyridine and sulfa-osalagine, and anticholinesterase agent, pyridostigmine used in the myasthenia gravis. So all these medicine like tubercular, antibacterial, anticholinesterase all contains the pyridine ring. Now proton pump inhibitor, omeprazole, lansoprazole, pantoprazole, and rabeprazole used in peptic ulcer all contains pyridine ring. Omeprazole, lansoprazole, pantoprazole, and rabeprazole. Now vitamin B3 and vitamin B6 contains pyridine ring, nicotinic acid or nicotinamide, and pyridoxal and phosphate. Now azepines, you know my friend, aromaticity here 1 to 3 positions, both conformation with 22 chair conformation percentage. Planar azepine nitrogen sp2 have a potential 8 electron system, cyclic and planar with 4 pi electron is an anti-aromatic character least stable. Thus, azepines and its tautomers exist in non-planar conformation, both conformation, one atom with the sp3. So, compound do not comply with the Haeckel's rule by electron, so azepine is non-aromatic compound. You can see 1H azepine, 3H azepine, 4H azepine, 2H azepine. Stability order 3H, 4H and 1H. Valence bond isomerization, you can see the from benzene, you can go very easily with the ring expansion and isomerization, you will get the 3H azepine. So from phenyl azide, benzazepine and 1H azepine derivative, you will get the 3H azepine derivative. From nitrobenzene, you will get the 2-alkoxy 3H azepines. You know the reaction, thermal reaction undergo at 200 degrees Celsius, then it lost the heterocyclic ring forming the aromatic ring N-phenyl carbamate. Ring contraction, you can see the product. Diels-Elder reaction forming a duct. Now medicinal uses anticonvulsants, carbamazepines and oxcarbazepine, you can see the contains azepine ring. Tricyclic antidepressant, imiperamines, diaceparamines, clopidamines and trimiperamines contains azepine structure. Now quinoline, 1-aza-naphthalene benzopyridine. Each carbon is sp2 hybridized planar. The total number of delocalized electrons are 10, 9 from 9 carbon, 1 from nitrogen. Follow Haeckel's rule, it shows weak bases and hydrogen bond. Now scrap quinoline synthesis, you can see glycerin aniline in presence of nitroaniline in sulfuric acid. You will get the scrap synthesis mechanism, formation of acrolein and the many steps you will get the quinoline. Dobner-Miller synthesis, the organic reaction of aniline with alpha-beta unsaturated compound to form quinoline. Now, Friedlander synthesis, chemical reaction of two amino benzaldehydes with ketone form quinoline derivatives. You can see the formation of 2-phenylquinolone. Electrophilic substitution, addition to nitrogen, formation of quinazolium salt and formation of methyl quinolinium iodide. So, electrophilic aromatic substitution benzene ring at 5th and 8th position. So, nitro groups at 5th and 8th, bromine group at 5th and 8th, and sulfonation occurs at 5th and 8th. Reduction, you can see the formation of 1, 2, 3, 4 tetrahydroquinoline in presence of H2 platinum 5, 6, 7, 8 tetrahydroquinoline. Now oxidation of quinoline, you will get the nicotinic acid. Reaction with the sodamide at high temperature, you will get the 2-aminoquinolone. Now medicinal uses, cinchona alkaloid, quinidines, and 4-aminoquinolines, chloroquine and amodiaquine, and 8-aminoquinoline, primaquine and bulgaquine, and this is the chloroquine. Now, quinolone antibiotic, ciprofloxacin, ofloxacin, norfloxacin, lomifloxacin, and sparfloxacin can quinolone antibiotic. This is quinolone. 8-hydroxyquinoline used as topical antiseptic. Now, isoquinoline, 2-aza-naphthalene benzopyridine. Each carbon atom is sp2 hybridized planar. The total number of delocalized electrons are 10, 9 from 9 carbon, 1 from nitrogen. Follow the Haeckel's rule, weak base and hydrogen bond. You can see the synthesis, Bichler-Neprelsky isoquinoline synthesis. 2-aryl enamine react with the acyl chloride or anhydride to form an amide. And this is the many steps reaction. So pictet game synthesis, modifications of Bichler-Nepralovsky methods, directly fully aromatic isoquinoline synthesis from two hydroxy substituted reagents. Now, Pomerange Frisch synthesis, acid bromoted synthesis of isoquinoline from benzaldehyde and 2,2-dialkyl ethylamine. You can see the electrophilic addition to nitrogen, isoquinozolium salt chloride, and N-methyl isoquinolinium iodide, and same way nitrogen get projected and chloride is countered. Now, electrophilic aromatic substitution occur at the benzene ring at position 5 in it. You can see the nitration, sulfonation, and bromination. So, reduction with the different condition, you will get the different product, 1,2-dihydroisoquinoline, 1,2,3,4-tetrahydroisoquinoline, and 5,6,7,8 tetrahydroisoquinoline. Now, oxidation, you can see the phthalic acid and pyridine, 3,4-dicarboxylic acid formation, and phthalimide. Chichibumin reaction, you can see reaction with NaNH2, it gives 1 amino isoquinoline. Now, medicinal uses, neuromuscular blocking agent, Curear alkaloids, atracurium, doxacurium, and margacurium, intracurium structure you can see here. Papaverine used as anti-spasmodic agent as smooth muscles contraction. Now, noscapines, antitussive cough suppressing agents, you can see contains isoquinoline. Now, acridine, you know the aromatic compounds 2,3-benzoquinoline, dibenzo, BE-pyridine. Each atom is sp2 hybridized planar, and total number of delocalized electrons are 14, 13 of carbon, 1 from nitrogen, and follows the Huckel's rule. You can see from diphenyl amine 2-carboxylic acid, you will get the acridine. This is the another method of synthesis of acridine, Bunsenstein acridine synthesis from diarylamine heated with the carboxylic acid and zinc chloride to form 9-substituted acridine. So, electrophilic addition to nitrogen, you can see acridine, hydrochloride, and 10-methyl acridinium iodide. Now, reduction, you can see the reductions of octahydroacridine from acridine and 9,10-dihydroacridine from acridine. So, acridine is undergo by permanganate in an alkali medium forming quinoline 2,3-dicarboxylic acid. You can see the quinoline 2,3-dicarboxylic acid formation. Now, Chichibumin reactions, you can see the formation of acridine 9-amine. Now, medicinal uses, tacrine is a reversible cholinesterase inhibitor and that has been used in the treatment of Alzheimer's disease. You can see contains acridine D. 9-amino acridine is highly fluorescent dye used as antiseptic and disinfectant. Now, indoles, you can see 2,3-benzopyrrole, 1H-pyrrole. Each atom is sp2 hybridized planar. The total number of delocalized electrons are 10, 8 of carbon, 2 from nitrogen, and follow the Huckel's rule. Now, Fischer indole synthesis, acid catalyzed rearrangement of an alkyl hydrazone to indole with elimination of ammonia. Reaction can be carried out simply by heating together the aldehyde ketones and aryl hydrazenes. The formation of aryl hydrazones and its substituent rearrangement takes place to give the indole. Zinc chloride is used as a catalyst. Look at the reaction scheme. Look at the mechanism. You can steps of mechanism. Now, Fischer indole synthesis, you can see from phenylhydrazenes. Bichler-Molu indole synthesis, you can see 2-aryl indole. Medlang synthesis, you can see this is the steps. Electrophilic addition to nitrogen, you can see the protonation occurs at nitrogen, 1H indolium cation, 3H indolium cation, more stable. Now you can see electrophilic aromatic substitution of indol favored at third position. So distribution aromaticity of benzene ring less favorable. Nitration, you can see 3 nitro 1H indol, sulfonation, acylation, manipulation, you can see formaldehyde dimethylamine. If you have the iminium ion, you will get the manic product. Here, the reductions, indolene and formation of 2 isomer. Nucleophilic substitution, you can see in presence of bully, you will get the substituted carboxylic acid and alcoholic. Now, medicinal uses, reserpine, antihypertensive of the late 1950 and care early 1960 to treat agitation, psychotic conditions, vinca alkaloids. You can see vinblastine, anti-cancer agent, and ergot alkaloids, ergometrine to prevent the bleeding after childbirth, smooth muscle contraction effect. This is the structure of ergometrine, ergotamine used in migraine. Now, indols, medicinal uses, sumatriptan and rizatriptan. Pindolol, non-selective beta blockers used in the treatment of hypertension and angina pectoris. You can see the structure which contains indol. Now, pyrimidine. You can see the position of nitrogen 1,3. Each atom is sp2 hybridized planar. The total number of electrons are 6. 4 of carbon, 4 carbon, 2 from nitrogen. Follow the Haeckel's rule. Now, from 1,3-dicarbonyl compound, you will get the pyrimidine. This is the another urea. You have diethyl malonate. You will get the pyrimidine 2,4,6 tribone, which is known as barbutyric acid. Pyrimidine 2,4,6 triol. React with phosphoride chloride with the zinc dust. You will get the pyrimidine. Now, alpha beta unsaturated ketones. You have chalcones, benzimidazines, dihydropyrimidine intermediate, and this is the pyrimidine. Now, from alkyl pyrimidine, 4-methylpyridine, you can see from chloropyrimidine, you will get the pyrimidine. Now, electrophilic addition to nitrogen, protonation occurs at both carbon, alkylation occurs one, so 1-methyl pyrimidinium salt. Now, electrophilic aromatic substitution, less reactive due to 2 nitrogen present in heteroskeleton. Reaction is possible at 5th position if ring is activated by electron donating groups, no nitration or sulfonation. You can see the bromination occurs. Synthesis, you can see pyrimidine, it gives pyrazole after ring contractions. Now, uses of pyrimidine in medicinal, fluocytosine, 5-fluorocytosine, antifungal agent, sulfadiazine, sulfamethazine, antibacterial agent. You can see the sulfadiazine which contains pyrimidine, trimethoprim, antibacterial agent which contains pyrimidine. Now, pyrimethamine, sulfadoxine, antimalarial drugs, barbiturates, phenobarbital, pentobarbital, secobarbitals used as sedatives and hypnotics. You can see the structure which contains pyrimidine, anti-metabolites, 5-fluorouracil, anti-cancer agent. Now, nucleoside, anti-metabolite, tarbabine and trifluoridine, antiviral agent. You can see the structure which contains pyrimidines, vitamin B1, thiamine used in thiamine deficiency. Now, purine, you can see each carbon is sp2 hybridized hybridized planar, and the total number of delocalized electrons are 10. So 5 for 5 carbon, 3 from nitrogen 1, 3 and 7, 2 from nitrogen 9, follow the Haeckel's rule, and basic in nature. So tautomerism, you can see 1H purine, 9H purine, 7H purine, 7H purine. Now, Traube synthesis, you can see pyrimidine 4,5-diamine react with carbonic acid, it give purine ring. So, this is the product. Now, from formamide, you will get the 9H purine 2-amine. From substituting imidazoles, you will get the 4-methyladenine. And electrophilic substitution to nitrogen, protonation occurs in alcarbons in one protonated predominant, and then butyl lithium, you will get the dimethyl purinium salt, and with hydrogen peroxide you will get the oxygen with nitrogen positive charge. Electrophilic aromatic substitution reaction is possible at 8th position. Oxy and amino derivative react readily than non-substituted purine. Now, nucleophilic substitution, you know nucleophilic displacement, whereas halides are most popular living group. Look at here, 8-chloro, 9-methyl, 9H purines, 8-ethoxy, 9-methyl, 9H purine. So, 6-chloro, 9H purine is give 6-hydrogenyl, 9H purine. Medicinal uses, nucleoside, anti-metabolites, acyclovir, valacyclovir and gnasiocyclovir, vidarabine, antiviral agents. Anti-metabolites 6 mercaptopurines, thioguanines, azathioprine, anti-cancer agent. All contains purine ring. Medicinal uses, methyl xanthines, caffeine, theophyllenes, and theobromine. Drugs used in the bronchial asthma used as CNS stimulant. You can see the caffeine, theophylline, and theobromines. My friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.